Good. So today is a bit of an application of all the stuff we set up on Tuesday, well, and before that, block entropies and whatnot, to elaborate what I had called in a much earlier lecture, anatomy of a bit. We had talked in introducing information theory for complex time series, complex processes, this idea of anatomy of a bit. We have a certain amount of information. That information gets stored, and some part of that is randomness, and some part of information relates to structure, organization, what we called back then redundancy. So we're going to make this much more precise today. This is probably the most detailed analysis of, when you make a measurement of a bit, the different kinds of information that can be either explicit or implicit in that bit of information. So we used or introduced on Tuesday these information diagrams. That's sort of behind a lot of this. It'll be a nice way to summarize this decomposition of a measurement, information in a measurement. And we'll be using the various kinds of multivariate information we introduced. I spent some time talking about possible extensions of multivariate mutual information. Even the kind of puzzling property that a three-variable mutual information can be negative. So I'm still trying to sort of get comfortable with that. But there were other kinds of information, bound information, local exogenous information, and then there was little tableaus, information diagram tableaus gave us some way of thinking about what these informations were. So we're going to apply all those today. Tuesday, they were just about having n variables. And trying to address this very broad question, what do we mean by correlation between n variables? And I think I mentioned then, this is still a research question. There's still a lot of very interesting open questions. Even simple things you can ask about the n variable setting and information n variables that we don't have a clue how to do yet, which is a bit odd. I mean, information theory has been around for a long time. We certainly have been doing multivariate systems for a very long time. It's just kind of fascinating. From the information theory point of view, there are a lot of open questions. So today, all we're going to do is take those ideas and make them much more concrete in the sense of applying them to temporal processes. So instead of a basket of n variables, we're going to have a block of variables over time. But by way of introducing this notion that the measurement contains different kinds of information, I just wanted to do a little bit of a deconstruction of what we sort of mean by making a measurement, and that contains information. So a little bit, I could have used this to introduce entropy way back when, the very first chapters of Cover and Thomas. Back then, it was mostly entropy and entropy rate were introduced by way of kind of this axiomatic formulation. A measure of information should have these properties, and then we derive the formula. There's another way to look at it, so of what entropy of a random variable is. Okay, so I want you to imagine that we have an instrument, and it outputs, when we ask for a measurement, one of k outcomes. Think of a coin, heads, tails. And if we wanted to store the measurement, we're going to have to go to Fry's or Best Buy and buy some memory. So since we have one of k outcomes, we can store that using log base 10 of k decimal digits, or our preferred unit here is log base 2 of k bits. Right? If we had k was 16 possible values, then I would need 4 bits of memory, binary memory, to store the results coming in. And of course, if I had a sequence of n measurements, then that would be the amount of memory, n times log base 2 of k bits of storage. But now I want to think of a different way. And we do have the sense that this might be too much storage, and we could compress that information sources have some redundancy, and we can come up with new ways of coding things. If we know a little bit what the distribution is, we can build codes that are easily decodable. Okay, so the first step in this. So this is sort of kind of a weak upper bound. That's the easy bound on how much memory we would need to store n measurements. Okay, so imagine, though, that you built a histogram. So we have counts here, the number of times event value 1 happened, 2, all the way up to nk. Or, again, think of heads and tails, k is 2. Number of heads, number of tails that we saw in the n measurements. Well, how many possible sequences of length n, say 10 measurements, would you have 6 heads and 4 tails? Well, okay, we know what that is. That's just n choose this multinomial expression. Okay, it was 2. If k was 2, then we just have a biased coin here, and that's just simply n factorial over the product of the individual count factorials. So if I tell you this length 10 sequence had 6 heads and 4 tails, there are many particular realizations, individual sequences, that satisfy that general constraint. So given us our histogram count of events, and the length, this is the number of possible sequences within that class of 60% heads, 40% tails. Okay, so how can we, now I want us to think about building a code. I want to come up with a bit string that exactly describes a particular realization. Okay, so again, what we're comparing against is n log base 2 of k bits, but there are things we can do, like, oh, let's just build a histogram of counts of the event values. What would the code look like for that? So here's what we call the description length of a histogram-based code. Well, I have now k bins in my histogram, or 2, like heads, tails. And then each bin, I have to anticipate all of the events being just that one particular value. So each bin, I have to store log base 2 of n, an integer that goes up to n, basically, and that takes log base 2 of n bits. So the histogram count is k times log 2n. Okay, well, that's fine. That specifies the class, 60-40 heads, okay, or 70-30, depends on the realization. And then we have log of m, right? I have to say which particular realization consistent with those counts occurred. So we just calculate that with a multinomial. Okay, so that's log base 2 of m. And then, okay, if you really want to get pedantic about it, I also have to tell you in the string how big n is. You know, this is a code where I could do 100 measurements or 10 measurements. I need to say, I need to put at least a few bits in there that is the number of measurements, so I can interpret this. And if you wanted, you could even say, oh, I have to tell you what k is, and so on. Okay, so dot, dot, dot. These numbers get smaller and smaller, but this is a very explicit histogram code for a series of discrete measurement outcomes. Well, let's transform this into something more explicitly in terms of n and k. Well, the way to do that is to apply Stirling's approximation to that multinomial. It's familiar in a lot of different areas, of course. So I'll do this in terms of log base, in terms of log. So log of m, I apply this Stirling approximation, just replacing all the factorials in the previous expression with this, appropriate even for n sub 1, n sub 2, and n sub k. Plug all that in, and I won't go through that. It's really a useful exercise because what pops out, I'm showing here the punchline, is you end up with something that looks a lot like, and you're just deriving this, so it looks a lot like p log p, right? If I think n of I over n is the probability of event I, that is p log p, even the minus sign shows up. Okay, so to make it positive. So this is, well, in fact, it's just this empirical estimate of the frequency of the events 1 through k. It's a distribution, so it really is just h, the entropy of that single variable. Interpreting as if, you know, these experiments were done in an independent way. So, in some funny way, Stirling's approximation has Shannon's formula built into it. So now we know an even better approximation of what this code length should be, this description length should be. Right? And again, the comparison we're making is, right before I said, the first cut was, oh, I have to, if I'm making n measurements, k values, I'd have to use n times log base 2 of k bits. Well, now it's n times h of x. So to the extent that the entropy rate is less than log of the alphabet size, we can do compression. Okay, so I'm just restating our arguments when we were talking about redundancy before, right? So here's, if I'm in my lab, I don't know much about the experiment yet. I have to go out and buy a certain amount of memory, raw memory in bits. So I'm telling you how to calculate them with a previous expression. I just have to store it, but after you've learned something, like in particular, if you've learned and you've decided to use the histogram and just count the frequency of the measurement outcomes, then actually the real information in the thing is h of x. So to the extent that h of x is less than log of k, you can save. Or the other way to say it is that there's this piece up here, which is the difference between the alphabet size and the single entropy, single variable entropy. That's the compressibility, or we call it redundancy. Well, okay, we also went through before that we're not even interested in IID processes so much, right? Most interesting process has some correlation over time. Therefore, the single variable entropy is going to will be a bad approximator of the true intrinsic randomness. And so we started looking at the entropy rate, which is this infinite word length growth rate. And we spent a lot of time interpreting that. So we have a similar picture, right? Now, this h mu can be less than the single entropy. Typically is, they'll be the same if it's multinomial, but typically signals have more redundancy over pairs and triples and so on signals. So now we have that notion of what we call intrinsic redundancy. It's log of alphabet size minus h mu, or in fact we call that specifically the total predictability. That was one of our constants of integration after we're coming down the entropy hierarchy. We integrated the predictability gain of all word lengths and not the total predictability. So in a sense, I know the alphabet size, somehow I figured out the intrinsic randomness size source, then that's the compressibility. So this can be a huge win. For example, written English, well, alphabet size of 26. Okay, so that means I have to, long text. And symbols, I have to naively store n times log base 2 of 26, somewhere between 4 and 5 bits per letter. If you actually do an empirical estimate of it, which people still do in a popular activity, even Shannon contributed to this, it's actually about 1 bit. The h mu is about 1 bit in written language. Okay, so this is just a setup. I'm recasting discussions we've already had in this way of thinking about raw measurement, and depending upon how we code things up, we can compress better and better until this absolute bottom line of h mu, and then the rest is, this distance here is going to be the compressibility, what's redundant in it. Okay, so what I'm going to do is we're going to today develop a similar kind of decomposition into informational components in a single measurement. What we're going to do is actually not so much compare to the raw alphabet size, but look at this compared to the single variable entropy, and ask what information that contains. Okay, so what we're going to do here, and I'll give you kind of a cursory overview first, and then I'll go show you where some of the conclusions, how they're derived. Okay, so what we've been doing is thinking about looking at the past and predicting the next symbol. But measurements also occur in the context of the future. So part of this decomposition is going to ask how much present measurements correlate with the future, not just focusing on how much the present measurement was anticipated by a past that we saw. Okay, so there's a first cut, and well, we're familiar with what h mu could be, the intrinsic randomness, and then there'll be a piece of the single symbol entropy which is anticipated from prior observations. So this is just a quick overview of where we're going. Okay, there's a certain amount of the randomness produced at the next time taken in isolation, but there's a piece of that could have been predicted from the past. This component could not have been predicted. Okay, well, we can actually go sort of one step further and break, for example, this intrinsic randomness up into two more pieces. There's a piece of this randomness, irreducible randomness produced in the present moment that the system just throws away, forgets it. But there's also a piece that gets remembered and affects the future behavior. So this is called the bound information. This is called the ephemeral information. We're going to end up with lots of colorful vocabulary here. Again, not pushing language too hard. You might ask, well, what's an example of this? Well, you can kind of imagine a process that generates randomness and throws it away. A fair coin does. A fair coin doesn't remember the previous flip by definition, but what's this be mu like? In fact, the original suggestion for this, or one of the original suggestions for this, a recent one, it's an older quantity, was something like in a music composition when you have a chord change. The actual moment when the chord change happens is surprising to you, but because you changed, or even the scale, then chord, then from that point forward, it sets a different context for the future. It actually has an effect on the future. So it happens randomly, it gets stored in the system, bound, and then it's part of the future, affects the future. And then this anticipated part up here, we're going to break it into two other pieces that get a little bit harder to explain. There's another piece of this anticipated predictable part of the single symbol information that is actually equal to B mu in the particular cases we're working, which are stationary processes. And then there's another called Q mu, which is something that's anticipated by the past, it's present in this moment, and plays a role in future behavior. And that can be negative.
Question?
Yeah.
So does that imply that the past, you don't need the current if you have the past to predict the future?
Oh, if it was all predictable, then yeah, then it would be redundant, yeah. Then the redundancy would be as big as...
because B mu is in H mu, and the only thing else in H mu is R mu, which doesn't predict the future. And then E mu is in the past, though, so the only part that predicts the future and the present is also in the past. So,
they are quantitatively equal, but they are not semantically
they're just equal
necessarily
in size.
equal. Yeah.
We'll get there. I'm just introducing a little bit of terminology and giving kind of a classic... No, that's fine. That's good. Right. These are amounts. They have different interpretations because this amount is part of this predictable stuff, and this is part of the unpredictable stuff. Okay. So. And then there's another interpretation, decomposition, where we kind of sum all these guys up and just kind of break it into stuff that gets forgotten and stuff that somehow plays a role in structural, we call structural information. Anticipated from past, the future gets stored in the past or future, and so on. So this is I think the key decomposition. So that's the synopsis. Now we're rolling up our sleeves. So like I said before, the setting so far has really been I was looking at some past and I tried to predict the future. Right? And our sort of quantitative version of that is that H mu is just the uncertain next symbol given the semi-infinite past. Okay. So in other words, we're interpreting that single symbol information in the context of the past. Well, these things have futures too, so what we're going to do is now think of the current measurement in the context of the past and the future, as if you could stand back and see the whole time series. Now that might seem to violate our physical notion of causality, but it's actually not that strange. If you have some experiment in the lab, you record all this data, it's stored on the disk, and you actually can scan backwards and forwards and look at measurements in the context of past and future. So it's perfectly practical setting to see how much of the information here not only is shared with the past, but might be shared with the future. Okay, so just some notation. I'm trying to follow the anatomy paper, the article we were supposed to read for this lecture. I'm going to change the notation just a little bit. We seem to change our notation about once every 2 years. So that so when I'm talking about a length L block, I use now a little colon here. Some of the past papers and lectures at the time, and then the length up here, they're all equivalent. So yeah, so it just goes. So this block, length L block, goes from T up to T plus L minus 1 up L. Now the past, and this is just being a little more compressed, we drop the index on the past side to indicate minus infinity, just a shorthand. Present is going to be x0. Well, the present could be any time, but these are dealing with stationary processes, so let's just call it x0. And then the future starts at variable 1 and goes forward. Again, I'm dropping the future side of the colon, the index, to indicate positive infinity. Okay, so very concise. Sometimes it's nice because it shortens expressions, but you have to be good at sort of scanning where the colon is. It's easy to kind of skip over first reading. Okay, and then just kind of a general shorthand here. We're going to be talking about the generalizations of these various n-way multivariate informations and mutual informations, but now in the block setting. And I'm going to have a number of different information measures. So whatever, think of some measure f, bound information of n variables. I'm going to apply that measure to a length L blocks, and then I'm just going to write that as a function, just like we did with h of L for the block entropy. Just think of it as a function of length. Okay. So, recall that the block entropy has this linear asymptote with excess entropy plus the h mu is the slope times L. And then here in our new notation, this is the mutual E, excess entropy is the mutual information between the past and the future. One of the things we introduced on Tuesday was called the total correlation. It was the sort of difference between the individual random variables and the joint in the collection. So we can do the same thing for a time series. So here's the time series version of this, block total correlation. Well, if we're looking at individual symbols and we have a stationary process, then this is just h of x at 0. Right? We're going to have them across the block in time, but they're all single symbol statistics, and that's the same at any time. So we have L times the single symbol entropy minus the block entropy or joint entropy. So there's a relationship between the block total correlation and the block entropy. And again, we introduced the total correlation. This is kind of comparing the entire joint process to the individual variables, the marginals of that joint distribution. And then here's what it looks like when you calculate it for sort of typical process. First of all, interestingly enough, it has its own linear asymptote. Without going into the details, the paper goes into the details of how these things work, but basically we have this offset, happens to be, one has to show this, that's minus the excess entropy, plus rho mu, that was that anticipated information I mentioned before, but there's a slope here, times L. So a block entropy does this, right? It's monotone increasing, goes this linear asymptote E plus h mu L, and then here in red is the block total correlation, and it has its linear asymptote. Now it has a different slope here, which is rho mu. So why do this? Well, it's just very easy to calculate word distributions and block entropes like this. We can pull out these different quantities. And that leads to the first decomposition that I mentioned. So actually, if you go back to the definitions, right, block total correlation had a minus h of L in it. So sum these things up, and it's just their sum is L, the length, times the simple entropy. If you plug in those asymptotes, right, so these asymptotes both, this is E plus h mu L, this is minus E plus rho mu L. The E's cancel out, and we just end up with this, what we divide through by L. So again, single symbol uncertainty breaks into a random part unanticipated by the past and a part that was anticipated by the past. Now that interpretation, you have to go back and kind of look at what the total correlation quantity meant. But in the time series side, that's the interpretation. And there are other generalizations of these end variable informations, right? So we had the bound information, the local exogenous information. Right, the bound information was if you remember the tableau, it didn't overcount like total correlation does the atoms in a four-variable information diagram. Treats them equally. Local exogenous information was the amount of information that a random variable is the total information that each random variable does not produce itself. The random information it produces that it expresses that comes from other variables. But in the block setting, time series setting, we end up with these block versions of these and variable quantities, and then it's just a little bit of algebra based on their definitions. Basically, just kind of just information identities again. So you can show that the block bound information is the block entropy minus the, remember, this is the residual entropy. It's all the entropy that the individual random variables produce that is not shared with anybody else. This enigmatic information I didn't introduce, but it's just the difference between the block correlation and the block bound information. And then the local exogenous is bound plus total correlation. Anyway, there's a little bit of work you need to do to go through and show those identities. And then you can look at them and say, well, what's their scaling behavior as a function of length? And it turns out they all, again, at least for the class of processes that we're looking at, finite memory, finite processors, stationary, they all have linear asymptotes. Now, this is obviously getting to be some sort of very over-complete description of what's going on, so no surprise there are actually relationships between these things. Here's the calculation of these block informations. They don't, they're more complicated, right? Total correlation, block entropy were nice, concave up or concave down, monotone increasing or decreasing. Here, the slopes are changing and so on, so they're a little more complicated in their behavior, and you might just say, well, look, you're taking all these sums and differences. Of course, you're going to get strange behaviors. So why do this? Well, okay, so now we have these different rates of growth. So they do all eventually settle down to some linear growth. And then I put in here their slopes, their asymptotic slopes, the names of the quantities I've already introduced. Yeah?
Those should be pluses.
Oh, okay, good, thanks. Yeah, there's not a negative slope to be seen. Right.
The Q could be negative, but it's still defined with a plus.
Right. So, yeah, I don't know where. Okay, there's a typo. Probably doing a lecture freshly. Okay. So, right. So the residual information has that R mu quantity. Maybe that's a little bit intuitive, at least given the previous interpretation. R mu is that part of H mu that is just forgotten. It's whereas the residual n variable information was that randomness that's not shared with anybody else, is just generated locally. And so on with these others. Okay, so this is just algebra. There's a few definitions going back to the n variable definitions and rewriting these quantities in for L blocks. And then you can easily write down these identities from their definitions, and then you ask, are there scalings? And all of them have a kind of linear asymptote scaling. So let's look at, just compare block entropy and block total correlation. Well, one of these identities is that H of L is bound information plus the residual. Given the previous definitions, we have their own little offsets. These offsets in the linear asymptote, I'm giving them bold E to indicate there's some relationship to excess entropy. We'll get to that. And then then we have, just summing up, for the slope of this guy, B mu plus R mu. Right? But we know that the asymptote for H of L is just E plus H mu L. Therefore, H mu breaks into b mu plus r mu.
That should also be a plus between the
Yeah.
sublinear and
Here.
yeah,
Sorry. Yep.
and similar in the
And algebra down here. Copying and pasting. Right. So, and then the excess entry breaks up into these two pieces, but that's just for definitions at this point. Same kind of analysis of block total correlation. It's the bound information plus this enigmatic information. Just plug in the previous scalings, and we see that, remember, TL asymptoted with a slope rho mu. That was that anticipated predictable information in the present. And we see that that is b mu plus q mu. And then there's another conclusion we draw about the relationship of these quantities here to E, right? Because T of L had minus E offset. So that's just the decomposition. This up here says that H mu breaks into this random component. Again, this goes back to the original definition of the residual entropy. And then this component B mu, which is this predicted piece. And then the second thing, we're looking at how block total correlation scales, these slopes give us this breakdown. So that's our second decomposition. Yeah.
Is that b mu the same quantity in both cases because of our kind of symmetry that we have between left and right time? That one's the everything going right, and one's everything going left. In a sense, our time series have an inherent order. Kind of.
Yes.
The past and the future are the same.
Oh,
due to stationarity.
yes, yeah, right. So that's the main property, that these quantities are the same. The formulas are the same, except you're applying them to different blocks. So they have a different particular information content, but the amounts are the same. They're stationary processes. Yes, I mean, I'm sort of hesitating to say sort of just swapping past and future because we're going to come to that next spring. And it turns out it's really interesting that there are properties that aren't time reversal symmetric, even for stationary processes. So that's a little hint, and it's quite curious and fascinating.
But if you take an infinite string of variables, what I call the past and what I call the future.
Okay, well that's a question. We just leave it open. So right, or actually here, I mentioned we just recorded all of our experimental data on a hard disk, and I shipped this to you in SneakerNet. You've got your gigabytes of data. You know, era of big data, that's actually faster than transferring over the internet. So I give you the hard disk, but then I forget to tell you, oh, the data is stored, was that the stack address going up or stack address going down? I forgot. So then you analyze it both ways. And the question is, is there any statistical difference in doing that? And I'll give, we'll guarantee it's a stationary process. So it's not the obvious answer there. It's really quite interesting. And we'll get to that.
I'm sorry, I missed that. So did you say that there are some asymmetric
Yes,
properties?
right,
for
right.
stationary?
Right. But we need to get into what do we mean by state, what are the hidden states. Also, there is a kind of an issue here that we'll come back to. Right now, what I'm kind of suggesting to you is a really practical way of thinking about these things. And I've got somehow enough data or some way of calculating the word distributions, and then I'm just going to calculate these block quantities. Well, even H of L is kind of hard because the number of sequences for a stochastic process, if it even has a little bit of entropy rate, the number of the sequences grows exponentially with length. So I'm kind of, the paradigm right now is, I'm just going to, hear the word distribution, I'm going to calculate P log P over that, but if you were doing this in an experiment, there might be some issues because if I have an infinite, exponentially growing number of events, I'm going to need an exponentially growing number of examples of them, so I can get good statistics on them, so I can calculate the probability as well. So yeah, I'm assuming some things here that we're going to come back and fix next quarter. The short answer is by building models from the data first. It's much more parsimonious than it's kind of brute force statistics. But for now, we'll just assume we have these word distributions. Okay, so, and we had one final quantity. No, the two final ones here, sorry. Right, so we have this local exogenous information, and it happened to be the bound plus the correlation informations. Same exercise here, plugging in the linear asymptotes. We see that there's another quantity that gives the slope of this guy. That is b mu plus rho mu. So that's over here. What we're saying is that W mu is B mu plus rho mu, or B mu plus Q mu plus B mu. Okay, so in this scaling, right, we already figured out what rho mu was. Okay, so that's our third decomposition. This more structural. These are, roughly speaking, kinds of stored information, whether it's coming from the past or the future. And then, you know, the complement is just this ephemeral information which gets generated but is immediately forgotten. So this is just another decomposition. It would depend, you know, which one you're interested in, and the applications questions you have. Okay, so then the final multivariate information is multivariate mutual information, which we spent a lot of time talking about on Tuesday, although it ends up in the time series setting to be, well, I don't want to say uninteresting, but at least for stationary process, pretty simple. So here's the translating the n-variable definition into the block setting, time temporal block setting definition. And you think, oh, there's some kind of linear asymptote with some offset, call it big I, L times some other scaling rate. Well, here's when you actually calculate it out. Empirically, you notice that, in fact, it goes to, well, 0, and the slope is 0, and the offset is 0. And you're going, no, well, why is that? Well, if you think back to this multivariate mutual information, one of the properties I mentioned was that, right? So this is the kind of this is the information in a group of random variables that they all contribute to. So if any one of them doesn't contribute, this number's 0. It's kind of brittle that way. If not everybody's participating. So here we are talking about stochastic processes and time series, and you know the kind of generic case we talked about exponential decay. If you just look at the 2-point statistics, two random variables, well, further they are separated in time, the less and less correlated, the more independent they are. Therefore, you know, sort of sufficiently long times, they will be effectively independent, and therefore they're not participating, and boom, this n-way or L block mutual information goes to 0. So asymptotically, because the sufficiently distant variables in the stochastic process become uncorrelated. So like I say, it's sort of like, it's a little bit disappointing. It's like, oh, it's just all zeros. Well, actually, this is sort of interesting. Something still to kind of study. Also, the current guess is this might be interesting for non-stationary processes, something we haven't really talked about yet. Yeah?
Boldface I is also, it's non-zero for periodic processes.
Oh, sorry. Yes, right. So this is all for right, stochastic. Some entropy rate positive, some, right. Yeah. Right, so then, okay, so the flip side of the argument I was just making, if it's a zero entropy process and periodic, obviously this chain of variables would be infinitely correlated, and they're all participating, and then you can, in fact, pretty easily calculate what these numbers should be. So, yeah, thanks. Okay, so here's the result of all of this. And again, we have a single measurement, we're looking at the present, and we want to know what kinds of information can there be? So now putting this back in the process I diagram setting that we developed last time. So here what I'm going to do is break here's the past in red, okay? And I'm going to break the future, at least according to Tuesday's notation, into the present we're looking at, and then the variables that go on. So now call this, starting from time 1, the future, x0 is at the present, and then before that is the past. So here in blue is all the information in the present. And before we looked at things, for example, we were interested in how the future overlaps with the past. And that was the excess entropy, right? Past future mutual information. Well, in this, I'm sort of privileging pulling out just one variable from the future, calling it the present. So if I look at the overlap with the past, it's these 3 atoms here. We'll come back to that. Anyway, so this is the summary of what's going on. You can't tell, right? So R mu, just kind of visually, it lies outside of everything. It means it doesn't share anything with the past and the future. That's why it's ephemeral. It just gets generated and it's forgotten. That's this scallop piece up here. Our B mu down here. This is information that's produced in the present moment. that has some correlation with the future. Also, there's an equal size piece to the stationarity, size b mu, that's correlated with the past. We have this other quantity here, q mu, very mutual information. And then there's this puzzling wedge down here. So I'm being honest, and when I write out this 3 variable, right, what are the 3 variables? Aggregate past, aggregate future, and present. There's this little wedge down here. We call it sigma mu. We'll come back to that. So anyway, this is the decomposition we just came up with. And there are different ways of thinking about this. So now let's just look at, we're going to focus in on just the way that past and future decompose the present. Just focus on that circle. So there's a, if you like, predictive decomposition. Right? So here we have entropy in a single variable. There's a piece that is shared with the past, a part that was unanticipated. Okay, so that's rho mu, that's h mu, the entropy rate. There's the sort of most detailed decomposition. The ephemeral part of that is d mu. So here, h mu, I split into these 2 pieces. It's q mu, very shared information. And then there's this piece over here. And these pieces here are also h mu, which is sort of interesting, because that's the piece that was unanticipated by the future. If I was looking in reverse time, right? Now the information in the present, here's my future. Hack that out, and I'm left over with d mu plus r mu, but that's h mu. So that's actually a quick visual proof that the entropy rate, the predictability of a random process, is symmetric in time, if it's stationary. Just kind of a visual proof of that. Well, we'll come actually prove it explicitly in the spring. And then finally, there was this so-called structural decomposition, just into basically information in the present moment that is somehow remembered or correlated with the past and future, and that's just chopped, thrown out, forgotten. All right, so that's what was going on in the present moment. But an honest drawing of the information diagram over future, present, and past, there was also this overlap. So what is this sigma mu? Well, first of all, it's outside of the present variable. So it's information that's not in the present, but it's in the overlap of the past and the future. So it's information not in the present, but that's shared between the past and the future. Well, to the extent this is non-zero, it indicates that there's something hidden from you, that there's actually hidden state information. And that information is not being captured when you make individual measurements. You might have to look at multiple measurements. So the kind of punchline here is that sigma mu indicates that you really should start doing some modeling, that you should start using, say, state-based models and try to infer some set of states that capture this, that kind of store this information. They're not observable, so they'll be hidden states. Some kind of hidden Markov model you should think of. Right. This is what I'm getting in the process's output, but there can be internal degrees of freedom that I don't have access to, and that's going to show up in sigma mu. Yeah?
Seems pretty related then to the initial ambiguity that we talked about a few weeks ago. I guess that would be sigma mu would resolve any initial ambiguity.
Remind me, initial ambiguity in...
So like we looked at sequences and we didn't know, or observed sequences in hidden Markov model, we didn't know what the state sequence was.
Yeah.
If we had sigma mu, we would.
Right. So in that context, that was sort of, we don't know what the start state was.
Sure.
Right? And we were trying to come to, like when we talked about the transient information, how much information do we need to extract to know what the internal state is? So it's that kind of hidden state information. Now, in that setting, we were assuming we had the model. We had the correct model.
Okay.
Right. So here, maybe it's kind of interesting in that all I'm doing here is I don't have a state-based model in mind. Not yet. I'm just doing, to kind of emphasize the point, kind of dumb block statistics. That's it. You calculate these quantities, and somehow this little thing's going to pop up if there's hidden state information. So you could kind of, in a sense, just kind of turn this quantitative crank, do your analysis of your time series, and then suddenly you make an estimate, you know, good or crude or whatever, fine. And would indicate, oh, maybe I have to look at a real model for this process. Capturing it in terms of single variable statistics isn't enough. And the same thing can apply if I had, you know, a block of length 2 here and so on. So that's just a hint. That's just a hint. That's actually a setup for the spring. So here, we're kind of exhausting. We've taken information theory and extended to deal with complex processes, well, beyond covariant Thomas means beyond IID, to deal with processes with general correlation. We're trying to calculate in detail as much that information theory can tell us. And we now have this nice kind of intrinsic semantic decomposition of bound information, anticipated information, all this, local exogenous information, and so on. And now this thing just kind of pops out of this and indicates there's something more we have to do. And that ultimately is the critique of pure information theory analysis of the system. And we have to fix that. Oh, and this I mentioned already. Again, you've just kind of, this is, right, if I think of the zero variable as the first variable in the future, and the red here is just the past, then the mutual information between the past and the future is in this overlap here. So the excess entropy, past future mutual information, is B mu plus Q mu plus sigma mu. So it has that little sigma mu piece in there. Okay, so that's kind of the sort of a pictorial introduction to the sort of theory of these information decompositions. Again, we're just making reference to blocks of variables. In this case, we just singled out one variable and called it the present.
Hey, Jim.
Yeah, Chris.
Quick question. How is being part of the mutual information between past and future? Is it conditioned on the present?
Right. So okay. So you have to kind of. So on Tuesday, what I did was just we had two aggregate random variables. I just broke the bi-infinite chain into a past and future. Past went up to say time -1, and the future went from 0 on out to positive infinities. And then we did a two variable I diagram, right? And I overlapped those two pieces, and that was the excess entropy. Here, I've singled out this one variable from the future. So if I want to ask what is E, I need to put this sort of back in. So it's really the future in the two variable sense we did on Tuesday is really blue and green. Okay? And then the past is just, however this past overlaps with that, will indicate the atoms that are part of E. And that's these three things. U mu, Q mu, sigma mu. Right? So yeah, so this is a kind of a slightly elaborated information diagram compared to just the kind of aggregate past-future one we did on Tuesday. Okay, so much for theory. How about examples? And Ryan, you should certainly chime in here. There are interesting things to draw, conclusions to draw from. I mean, it's one thing to sort of motivate this graphically, and there are kind of these general interpretations, most of which I think one has to go back to the end variable information discussion to understand how these interpretations arise from those original definitions, and then see what they mean in the time series setting. But here are some estimates of these quantities. So for the even process, golden mean, and noisy random phase slip, so we call this the noisy random phase slip. It's basically period 5, except there's this isolated branching on a 0, 1, therefore we call it noisy phase. And then up here, every once in a while, A goes back to itself and kind of breaks the exact period 5. So that's the phase slip. So that's what it's just NRPS to us. Okay, so single block, each mu rho mu. So we're doing this in terms of these different decompositions. So single site statistics, 0.9 for even Golden mean is the same, very close. All that's different are the labelings of the observed symbols. And RPS is a little bit more random. So again, this single site breaks into these two quantities, HU and rho mu, and you can see they add up to that. Now the really curious thing about, and there's not any difference actually between the golden mean and even in terms of the split between what's anticipated from the past and the randoms generated in the present. Same numbers here. These processes look equally unpredictable, or equally predictable, depending on which one you want to focus on. What's interesting, and this shows why we just went through all that rigmarole, is the difference in these other more atomic measures. So the ephemeral information, right, this is randomness produced in the present, that's forgotten. For the even process, there is none. All the randomness it generates, well, it's got to show up here in d mu, right? These two numbers have to add up to this guy, h mu. So all the randomness that's generated gets remembered. Whereas over here, for golden mean, there's some kind of split. There's mostly information generated is forgotten, and there's a little bit that's remembered. And you can kind of convince yourself of why that's true for the even process. It's a little harder to look at the golden mean machine there. But here, it means that, in some ways, an individual symbol is predictable from both sides because of the structure.
Do you want to go more into that? Or?
If you want to, yeah. You have a favorite explanation of this.
So that quantity, the quantity R mu, was originally proposed by Weissman and Verdun as a measure of non-reconstructibility of binary erasure channels. So you covered those, right?
We covered a couple different channels, not the erasure one, but yeah. Close to it, yeah.
Binary erasure channel is when you throw ones or zeros through it, and sometimes that symbol gets erased and you just get a blank instead of a corrupted value. It's just nothing. And so what it really quantifies, or at least the ratio of R mu to H of 1, it quantifies if you had your entire time series written down and erased one spot, how often you would not be able to fill that in based on its context of the past and the future. And so for the even process, you can always fill it in due to the constraints. Imagine just some long series, and you erase some symbol. If it's a 1 that's in the middle of a block of ones, you know you'll have an odd amount on one side or the other, and so you have to be able to put a 1 there to make it consistent with the pattern. If you erase a 0, again, if it's on the edge of a 1 block, you know adding a 1 there would make it an odd number instead, an odd number of 1s, and so that would break the pattern. And if it's in the middle of a bunch of zeros, then you can't have an isolated 1 due to the pattern, so it has to be 0. It said it has to be 0. And so anywhere you would erase a single symbol, you can fill it in based on the context. Right. And you can do that sometimes with the golden mean. For example, if you erase a symbol that's next to a 0, you know it has to be a 1 because you can't have 2 zeros in a row. But if you were to erase a symbol in the middle of a block of 1s, it could be a 1 or a 0. So sometimes you can fill it in, sometimes you can't. And R mu quantifies that. Or it essentially quantifies how often you can do that. Or how often you cannot fill it in, actually.
Yeah. Mm-hmm. Yeah, great. Sure.
R mu over H1 in golden mean process is 1 over 2. So does this number...
Is it exactly 1 over 2?
For the golden mean,
I can find out.
yeah, add them up. W mu. I don't know what to think about that.
Does it show something? You have 2 options maybe for this Mont Blanc.
It's not that simple, I think.
Yeah. Right. So you're saying that the single symbol of entropy is twice that. Yeah, you're right. No, it's easy to see. Sorry, it's exactly that. Yes, that's curious. I don't know. But we're figuring out. So okay, so what we're doing here is just to kind of say this. What the exercise is. The exercise is to take the even process and pretend, write out a string, and then as Ryan was saying, go in and just knock something out. And given that you know what the structure of the machine is, you don't know what the branching transitions are, but it turns out that whatever you erase is all the time is. You can fill it back in. You could sort of imagine this is like a code that is, if you had a 1-bit error, you could fill it back in again. So, whereas that only happens sometimes here. So, yeah, and the other curious thing is notice that this mysterious sigma mu, right? So this is the information not in the present that's shared between the past and the future. It's basically maximal or very large for the even process, and it's exactly 0 for the golden mean. So what could that indicate? Remember what the difference was between the golden mean and the even process? Right. The golden mean is an order 1 Markov chain. So it presents all of its state information in the sequences. The present contains that information. Here, right, we had this non-Markovian, or finite state, even process. Right? This is an infinite order Markov chain. Therefore, there's a lot of information hidden in the states that you don't have access to that goes not through the present, but through the states to get from the past to the future. So again, the point here is, it's really presenting it as if it was just a crank to turn. You imagine that you've got some process and you start with the word distribution. You just calculate these numbers, and then you're starting to see that these interesting, just from like the quantities and what's 0, what's not 0, you're starting to understand how the processes are storing information, how hidden are they, how unhidden they are, and so on, just by looking at the numbers. Without having to, then you go back to the model. If you generated and made the model, you can maybe see if that's consistent with that and how that gives you some insight into it. So again, just to give some more examples here. Golden mean process. Now what I'm going to do is vary the self-loop probability between 0 and 1. So when the self-loop probability is 0, it's basically period 2. Right? So it doesn't take this loop. It just goes 0, 1, 0, 1, 0, 1. Okay. And then what we're plotting here is this upper curve is h mu. It's called a stacked plot. And then this distance is r mu, and this distance is b mu. Right? So they add up to h mu. So what happens down here? What you see is, well, first of all, as the golden mean gets more and more biased, it becomes period 2. It's periodic. So h mu is going to 0. But you can see that the largest fraction of h mu, of the randomness generated, is b mu. It's information that is being created, and it's mostly being remembered because it's in the bound information. Well, what's going on here? Well, it's period 2. And so what you're seeing here is that h mu is mostly b mu, and r mu is equal to 0. So what's happening is that we have this period 2 process, and occasionally it's injecting a little phase slip by very rarely going to A. But that has an effect on the future because we have this nice fixed period 2 phase, and then every once in a while, randomly, this random information shows up and screws up the phase, shifts it a little bit one way or the other, which has an effect on the future. Right? It might be at even times I had the 0 and odd times of 1. I do a little A loop, and suddenly it's just exactly the opposite. So that I exactly flip the phase. So B mu is the largest component of H mu. It's kind of in a complementary way, when the self-loop probability is 1, mostly this guy's just taking the self-loop. It's generating this long block of 1s, this long sequence of 1s. Occasionally, right, I get a little jump down here and I interpolate as 0, 1. But then it goes back to being all 1s. So in this case, the information that's generated is mostly army. It has an effect, makes it hard to predict, but it always goes back to being all ones. So it doesn't remember that. It just occasionally happens in this long string of ones, but it doesn't get remembered because the future is just ones. It doesn't remember that you interpolated it as 0, 1.
It's essentially a highly biased coin.
Yeah, very biased coin. So it's always going back to the largest probability symbol. But that largest, since it's all ones, it can't store any information. Like the previous case, it had some phase that could store information as it went off into the future. Here's the logistic map. Really nice diagram that Ryan made. So what we have here, it's a stacked plot again. So this is, again, so this is a logistic map going from 3.55 up to r equal 4, where it's fully 2 on to 1. We have here essentially h mu at the top here. This is the r mu piece, and this is the b mu piece. So again, and then this is our bifurcation diagram for geographic reference here. Well, okay, so the it gets more and more random as we increase r. We know that. We did the Lyapunov exponent, which is actually equal to h mu in this case. We see the periodic windows. It all goes down to 0 because these are periodic. Behaviors, period 3, period 5, period 6. This h mu goes up to 1 here, fully to 1 to 1. That's our Markov partition case. Notice that now that r mu gets very large, or the other way to say is b mu goes to 0 here. It's like a fair coin. There is no memory in the process. Curiously, right here at band mergings, we also have a similar kind of increase in h mu. But also, if you look down here at the band mergings, b mu goes to 0. And you can actually kind of show by modeling what's going on with these band mergings. 1 band, 2 bands, 4 bands, same thing happens down here. It's a little bit noisy down here numerically. But in between, right, we have this, so between the 2 bands merging to 1 band, so we have, and that's so similar to each one of the other branches here, we have this very complicated trade-off between the total uncertainty, total randomness being broken up into different fractions of what gets remembered and what is thrown away. Really complicated. We're still working to understand that. Probably the nicest example to study the contrast is, if you remember, the tent map. Tent map, we know exactly what h mu, or the Lyapunov exponent is. It's just log of the parameter a. So that's here. But we still see this really complicated interplay between r mu and b mu. Right? The value somewhere up around here, where we have very large amount of h mu randomness that gets stored in the future, affects future behavior. So this is kind of unsullied by the complications in the logistic map, where we have all those periodic windows and so on. It's also clear to see at band mergings, where it goes to 0. You can't even see the bifurcation diagram. Again, and the self-similar in the bifurcation diagram means these behaviors are the same, just rescaled. This, I mean, this looks like some kind of fractal, non-differentiable curve. Probably is. But we're still working to understand why we have this magnitude of b mu up here. Exactly what topological features in the map, as you vary the parameter, are causing these very strange variations in the bound information top.
Going to 0 at the band merging, do you think that's when we can actually have a Markov partition?
Yeah. Well, and a particular kind of Markov partition.
Okay.
Yeah. Right. You have a Markov chain that's simple, very simple.
Right. There are other places with Markov partitions where b mu is not 0.
Yeah. In fact, one of the analysis that Ryan's now doing is this one, right?
Yes.
Right.
I think so.
So we have, of course, this is anticipating what the spring is all about. We have a way of discovering what the effective state machines are. And then from that, in fact, most of these calculations require having this representation. You can calculate these quantities fairly accurately and then try to understand in detail what the mechanism is, right? So HMU is saying, oh, there's some kind of branching structure, state-to-state branching structure, but then some piece of that spontaneously generated information is somehow being remembered, and say by distorting the state distribution or something like that. So we're trying to figure that out. So that's hopefully we'll figure it out before we finish writing the paper. So, yeah, Greg, sorry.
So on the logistic map, is there any places where HMU is completely B-mu?
In the limit, I believe at P infinity they might be, but they're both 0.
Oh yeah, yeah.
In the limit, it
Where
might
there's
be.
0, yes. Where there's
Well,
0.
I think in the limit, so just past it, they're
Yeah.
approximately equal.
Really? Oh,
I don't know.
I don't know. Good question. I would sort of suspect not. But that's a good question. Why, make a one-dimensional map that is sort of the analog of the even process, and then it would all your HMU would be B-mu. I've never found the even process in the logistic map. Could be there.
This would imply it's not.
Yes. Right. Yeah. Yeah. Well, unless there's some.
Yeah.
Really. Yeah.
Measure 0
Infinite
kind of
spike. Yeah. In the parameter space. Yes. Can't exclude it, but it's highly unlikely. Okay. So again, and then these examples with the one-dimensional maps just shows you. Well, partly we can calculate these things. So of course, that brings up the issue of how do we calculate them? So we need some more tools for that. That's spring. So let me just give a little bit of a reprise of what we've been doing, sort of most recently. I sort of promised when we first started talking about information theory that I wanted to convince you that information is not this unitary thing. In fact, they're just different kinds of information, and the way I like to frame it is they're answers to different questions. But hopefully in the detail that I've been able to lay out, you can see that there's at least a consistent framework for answering a wide number of different kinds of questions. And like I was just trying to emphasize, sometimes a tool is useful if you can, in a complicated situation, apply it blindly and then have the numbers come back and tell you, oh, there's a hint of something going on inside. So, but anyway, by way of summary, right, uncertainty, surprise, randomness. Now those words have some sort of quantitative and well-defined mathematical meaning: compressibility, redundancy, transition rate, mutual information between channel input and output, memory, well, excess entropy. I put memory in quotes here because it's actually not a form of memory, although I've been saying that all the way along because it's the easiest common word I can use. There's actually a puzzle behind this. It's not the actual stored information in the process. Measures of synchronization with the transient information. We have RMU, ephemeral information, bound information, and so on. So there's this very detailed view that information theory can give you when you look at complex stochastic processes, sort of arbitrary, in this case. Stationary, finite memory, although we did talk about infinite memory cases. And this has a kind of a practical analysis procedure attached to it, right? I mean, so here, we studied dynamical systems, closed the box up, talked about how measurements, or a sequence of measurements, could be good indicators of what's going on inside. And then we spent most of the last half the quarter trying to figure out what kinds of statistics and information are just in raw processes. What we haven't done is this. There have been hints, like when sigma mu is positive, that there is some overt, there is some information, hints of information in the observations, but that indicate there's some internal structure in the process. So we're not building models yet. Nonetheless, and I'd sort of say that the talk today was certainly in implementing this pipeline, right? All of this sort of assumes that you start with the word distribution. You estimate that empirically, or maybe you have a model, theoretical model, you can calculate these. And then, this can start with some dynamical system or stochastic process. We can talk a little bit about spatial systems, cellular automata, and then you have to be careful how you design the partition of this. Now, hopefully there's this issue of just plugging an instrument to your experiment can be problematic if it doesn't partition things up well that match to the dynamic. And then from that, we just end up with getting the word statistics out of this, and then we can go through and calculate these various quantities to figure out information produced, how random it is, how much stored information, how hard is it to synchronize. So we've actually kind of covered a huge amount of territory. I appreciate your patience and persistence and sort of holding on. Right? I mean, remember back to the beginning, right? We were talking about, well, actually we talked first about basins of attraction and attractors and invariant sets, particular kinds of invariant sets we thought were interesting. These chaotic attractors gave a definite geometric definition of what chaos is in terms of positive Lyapunov exponents, the whole spectrum of Lyapunov exponents. Looked at how they change from one complicated behavior to another. So these dynamical systems can produce complicatedness in different, distinct ways. Which attractor you're going to, is it chaotic or not, and then how does everything change as I change my experimental controls. But the key was to think about them, I think. Well, there's this question. Okay, so they're complicated. So what? What am I going to do with that? Well, these things are, I think, most usefully interpreted as information generators. So that's the motivation for using information theory. Right? They generate randomness, and they also have various kinds of information storage. So the entropy hierarchy, taking the block length derivatives of the block entropy, the entropy convergence, and so on, kind of got us started thinking about that there are these different kinds of information, predictability, redundancy, excess entropy, and transient information. So hopefully that is a somewhat consistent picture of how you can think about complicated processes. We don't necessarily have to think about deterministic dynamical systems. They could just be, certainly all the information theory we were talking about was pretty much just any kind of structured stochastic process. It's finite and stationary, so much wider application than even just nonlinear dynamics. But there are a whole bunch of questions. In fact, I kept trying to have to moderate, or maybe I didn't. Maybe I didn't moderate myself at all. I kept hinting at what's going to happen in the spring, because that's really the, I don't know, maybe I can say it now, the last lecture, almost more interesting. There are a bunch of questions that we kept coming right up to the frontier of. So what's a model? Well, we introduced that mostly because I got tired of saying stochastic process, and it was just easier to describe what they were doing by giving state-based models. But that begs the question. Again, if you think of that data analysis pipeline, if I just give you the data, how do we build a model from that? What are the effective states? What's the dynamic over the state space? What are the transition matrices? So far, we've just assumed we had those. And we thought of, when we have a model, it kind of generates data. Well, there's an inverse problem. Given data, how do I get to a model? Now, human beings, scientists have been pretty successful at this, right? Science over the centuries has built models and is kind of curious that in some ways it works. But it's pretty much a trial and error, kind of ad hoc approach. Well, when a domain, think of, planetary physics, kind of finally gets a good handle on the basic observables and what the basic forces are, then you can start to make a lot of very particular quantitative process. But what about new fields, right? If I give you a string of DNA, I didn't have you go through all the biochemistry and molecular biology to hear about translation hardware, how would you figure out where in the DNA there were interesting pieces of AGCT, or blocks of them, right? Base pair triplets code for amino acids, right? There's a reading frame. Could you detect that in the DNA sequence? Could you have done it? Well, that was done in a backwards way by figuring out that we already knew we had proteins, and then amino acids, and so on. So this is just all these issues beg the question of how we discover these models, effective state space and the dynamic to start with. So that's the main goal for Spring, is to show that there are positive answers to this. There is a way that the data that you have tells you how it should be represented. And if you're kind of willing to buy into this picture, you suddenly start realizing how often the different disciplines in science aren't so much using the correct representations. It's more a community of understanding that has a certain set of accepted models, and they impose those on the phenomena that they study. Right? And you can't get the kind of power of that until you know that there's a principal way of going from data to discover what the models are, what the right representations are. So it's really the main thing. And it starts with a rather thoroughgoing sort of deconstruction of what we mean by state. I mean, we have to roll back. I mean, we've been using that concept really a lot, but there's something we don't understand about that. So we need to introduce a way of discovering states. And then this kind of dovetails into issues of statistical inference. What do we mean when we're looking at a system? What cause and effect are? So we'll talk about causal explanation, causal modeling, and talk some more about some applications. Kind of depends. The last half of the course will be when you folks break into doing projects. And then the lectures will be more like research seminars, and we can kind of choose different areas to look at. We could look more at cellular atoms, complexity in space-time. We can look at complex materials, or class of one-dimensional materials. We've been studying from X-ray diffraction spectra, having a whole new theory of how there's actually ordered structure in what appear to be noisy crystals, noisy materials, and a wide range of other applications. Probably the main punchline, though, is to get to a point where there's a duality. So this would be kind of the main philosophical point. At least it's the way I think about this stuff. That there is kind of a notion of information processing, inherent information processing, what I call intrinsic computation going on in nature. And this is complementary to what I said before. Usually a physical view is, oh, what kinds of energy are there and how are they transduced? So we have this notion of intrinsic computation in any stochastic or nonlinear process. And we now have a bunch of measures. You can say what these things are. Now, this notion of intrinsic computation is not running your Excel spreadsheet and filling in your tax numbers and hitting return. It tells you you owe the IRS $1,500. That's what we call useful computation. That's actually kind of a joke, but this is when I say intrinsic computation. This is not referred to an observer making some judgment, like me when I have to write out the check to the IRS. Right? It's how much of the past is stored by the process. What internal organization is used to store that information, and how is that internal stored information used to produce future behavior? So that's the definition of this intrinsic computation. So, and then it turns out, so this duality is that this notion of intrinsic computation is a quantitative proxy for how processes are structured, what the patterns are in the process. What we mean by organization actually gives a series of measures of organization. So what do you mean by organization? Sort of regularity, symmetry, there are all these kind of words we use. But you can show that when we start doing this intrinsic computational analysis of a stochastic process or dynamical system, what we end up discovering are its inherent symmetries and partial symmetries, basically how it's organized. The group structure, algebraic structure, and the so-called semi-group structure in the process. So the punchline is that how nature is organized is how it computes. So that's the duality, that there's this interesting complementary relationship between structure in the world and how information is stored, processed, and generated. So that's the product placement for this spring quarter. You should all sign up for it. So again, thanks for your patience. Covered a lot of territory.